C, we assume that C is a regular curve. It's actually not needed in this proof. It's only needed for the length, because here we divide by C dot of tau. So if C is not a regular curve, then that might explode. So C is only needed for the variation of L. Not of E. And problems like that are usually the reason why the energy functional is slightly better behaved than the length. One more remark, which is like, I will not write it down, it's just like one very side remark. It's like one of the motivation that I gave here was to say, okay, we look at these variations as like a curve of curves, where you have like a variation in the sense of that it would be a tangent vector at the space of all curves. And there's actually a way to make sense of that. But it would require that you say like the space of all curves, like say with given endpoints, is something like an infinite dimensional manifold, or like an infinite dimensional surface, like a thing that is like has a lot of degrees of freedom, but you can still do a differential geometry like what we discussed. And actually that's possible, and that's what is called infinite dimensional geometry. That's one of my research areas that I'm interested in. So here you see one first glimpse of like how such infinite dimensional stuff come in, which is like something comparing functional analysis with geometry, is where you look at like certain functionals that depend on geometric structures. Here we have like the functional that depends on the curve. And that's very similar to some problems in physics where you also have like, say you have like a surface and you want to change the surface and say like, which is like a surface that is minimal or like something like that in a certain sense. So that like gives you a certain kind of problems that are all of these kind of forms where we have like a variation of the geometric structures. So that would be the C of epsilon here, but it could be also something else. And in all of these cases, you have something like infinite dimensional differential geometry lurking in the background. And then this problem here, what is like saying, is kind of, you can make sense of that in this infinite dimensional framework, would be saying that the energy is a nice smooth function, but like the length that has like certain problems if the curve is not regular, says that like the length is actually not a smooth function. It's not smooth exactly at points where the curves, like the points which are curves, in this case the curves are not regular. So that's, yeah, just like as a like very tangential side remark. Okay, so let's come back to our original motivation was to have this question: when is the variation of the length actually zero, and what is the connection with geodesics there? And that's the following big theorem that says that, let's see, the curve in S with constant speed, then C is a geodesic if and only if it is an extremor of the energy and length functionals in the sense that we have d of epsilon goes to of EC of epsilon is 0 for the energy and for the length of these variations for any smooth variation. C of epsilon with fixed n. So that answers in some way exactly this question that we had, namely C is a geodesic if and only if it's an extremor, so either like a maximum or minimum or a saddle point of the energy and the length functional, in the sense that you take the first derivative of the energy and the length, you get 0 regardless of in which direction you take. So one way is clear from this proposition is that if you have a geodesic, then you get this expression over here, this covariant derivative of the tangent vector that is 0 for a geodesic. So in this case, you automatically get that this variation of the energy and the length functional has to be 0. So that's the easy way once you have these formulas. So this direction is clear from previous proposition, since the covariant derivative of the curve is 0 for a geodesic. So that's the one direction. For the other direction, we assume that we have not a geodesic. So we assume that this expression is not 0. Then we can realize that it's a vector field along the curve. So if that would be non-zero, then we can just take a variation in that direction that is given by this vector field. C of epsilon with variation vector field V given exactly by this expression. But then, if you calculate the dd epsilon in the of the energy in this for this particular variation, we have to look at the formula up there, and now we insert for v of tau, we insert the covariant derivative of the curve again. So here we have minus, and then here we get the covariant derivative of t, and then we get a second time the covariant derivative of the curve, and then we integrate over time. So that's just the norm of the curve, and by assumption the curve, like this vector field, was not zero. So that means the norm has to be strictly positive. So that's a strictly positive number, and then we get overall that this variation of the energy function has to be strictly negative. So what we get is that the energy variation is strictly negative. And that means that along this C of epsilon, we actually decrease the energy. So if you slightly change like C in the epsilon direction, then you actually get like a less energy. But that was like, not possible because by assumption C of epsilon was an extremol. So that means that it's not possible if d of d epsilon is 0, of C of epsilon equals has to be 0. So like that's the second point, right? Like we assume that we have a like an extremal point, so that would be 0 for all. Then we get that it automatically cannot have like this a condition. So contradiction. So that means that if we have an extremal point, then we also get a geodesic. And that's it's a common trick in this kind of settings where you choose like the variation in a certain way to derive like a contradiction or a statement that you would like to have. So that's the proof. And with a little bit more work, which I will not show, we can also get like the following corollary. Says that every point P has a sufficiently small neighborhood U such that there's exactly one shortest connection from P to any Q out of this neighborhood. And this shortest connection is a curve, and C is then a geodesic. So this corollary essentially says that locally geodesics are minimize the length or the energy. So the picture here is we have every point, say we are given a point P, then we choose some neighborhood, which is U, such that every other point in the neighborhood has something like a straight line, which is the geodesics in there. And we can do that for every point in U. But it's important that there's like a U around every point, and that U depends on the point. So like some points might have like a slightly bigger neighborhood, and some other points have a slightly smaller neighborhood. And it's important that in this context that it's locally. I let you think for a second while I clean the backboard. If you can find out like an example of like some surface where you have two paths which has like different lengths but connect 2 points, and both of them are geodesics. So one example would be the sphere, for example. So globally, it doesn't have to be the minimizer. For example, on the sphere, can be connected by many different geodesics. So that would be geodesics are the great circles. If you have 2 points on a sphere, so let's say I have these 2 points, then there are many different ways to find like a great circle that goes through these 2 points. Namely, for every third arbitrary point that I can choose, then I have one great circle that goes through 3 of these points. But like where I put like the third one is completely up to me. It's like one would be maybe you can choose the one that goes around like this, but you might also find like a different path where you just like rotate this point back here. Don't know if the picture gets more clear, but so you can like just choose a different point, and then you get a great circle which is given by the third point, and then there's a unique great circle that goes through 3 points. So what you're missing is essentially one other point that gives you the great circle. So you get a whole family of great circles, and not all of them have to have the same length between these points. That's the... So perhaps it's better to think of geodesics not really as minimas of the length functional, but more as like saddle points of the length. So that's also like the theorem like that we got up here was that saying that like the geodesics are exactly these ones which have like 0 at the variation. And from your geometry or calculus course, you know that if you take the variation of the function and you set it to 0, what you get are saddle points, not necessarily maxima or minima, but like in general, you might get saddle points. And like this kind of example of the sphere shows you that there really might be a different geodesics with different lengths between 2 points. But this property here, that's usually what people mean when they refer as like geodesics are minimizing the length. And there's a global version of that corollary, which I want to just state. Which is called the Haupt-Frino theorem. So the setting is that like that S be a connected surface. Connected here means that every 2 points can be connected by a smooth curve. So most of the surfaces that you look at are like of that form. So you don't want to consider like surfaces that are having like essentially these kind of properties where you have one surface and this different surface, and you consider them as one that you're like just like say, okay, this one is like one surface now, because here the points in this surface you can't really connect to this part of the surface. So we want to prevent these kind of like situations. So these were what is called connected. And now we have an important assumption, namely assume that every geodesic exists for all times. all times. And I will comment on that assumption in a second. But then the proposition or the theorem says that then for every point in the surface, there exists a geodesic C from P to Q that minimizes the distance, namely the distance between P and Q, equals to the length of the curve. So it's like similar to this as to this corollary, but now we assume that it's not like we have a small neighborhood, but like it's really the whole surface. And a comment about this existence problem. For example, take like some part of the plane. So if our surface would be this, and we choose some point P in that direction, then we know that the geodesics are just straight lines in this direction. So now I'm very mean, and I say like, I consider the surface, but I remove one point, which is like happens to be exactly in the straight line from P that is like that I chose. Then the geodesic is still like a straight line in this direction, but it's not defined for all times, because at some point it will hit this point which is no longer an element of the surface. So at that time, the geodesic will just stop, and you can't continue the geodesic in this direction. So. And that means that if you now choose a different point, which is laying essentially on that line, so I continue that line and choose my point Q here, then we have a counterexample to this theorem, namely I can still connect P to Q by some curve, which would be like I can still connect P and then walk around here and then go to Q, but I will never be able to make like the distance between P and Q to be the length of this geodesic that I choose here, because I always have to go around something. So like there will be some small deviation from the length, so that's whatever connection I choose between P and Q, they will always have like a length that is strictly bigger than the distance between P and Q. As the length of the curve is strictly bigger than the length from P to Q. So in this case, we don't have like a minimizer in the sense of that really that there is a curve that assumes this minimum. Okay, so I think it's a good moment for a break. So let's continue in 15 minutes, which is 5 minutes after half past. And then we talk about like certain coordinates that we get from these geodesics.
How can we prove the color? We can apply only one geodesic in the local.
Oh,
and
like the proof is essentially like the same kind of idea that I showed like in the second part. Is that you assume that there is a different geodesic, and then you derive a contradiction that it's like the extreme. So that's so the point is that you might have like a geodesic that is minimal. If you change that geodesic, then you actually get like paths that have like smaller. So it's not a minimum, but like the you have the infinite dimensions that goes like yeah. Like really like the sun. It's like you have a certain direction where that's longer. That would be if you change that path to something that is no longer a geodesic. But you can change these geodesics slowly so that they like are geodesics. But like yeah, like the length actually. Maybe like there's even like the example, like you just take two dimensions, you have like here a point, and you take here the point, and this part is a third element, you just start and draw. But you have both parts of the bigger. But this part, this length is definitely bigger. So in this case, you really have like one third element is not in the So that's like a simple example, it's a counter example to the global minimizer, but like there's a nice part of the expression here that you change that of the circle slightly. Is that really that it shows that there has to be some like always equal to the like two minimas which are local. Hopefully still be that that's the length. Like one of them, the short one would be here, and the other part, and both of them would be able to be, but like this example here, that we can actually turn one and have many different visual messages that are kind of specified point, actually shows that it's not like a platform, but not really a So maybe it's best to read it like this. So you assume that you have dd epsilon of the energy is 0. So that's like in this direction, you assume that you have dd epsilon is 0 for all variations. And then you assume for contradiction that you don't have a geodesic. So if you don't have a geodesic, then we can take whatever this vector field, which is like just one vector field on the curve. That curve, you take the vector, and then you calculate this vector field. And that one is not 0, so it looks like maybe like what you then do is you take a variation, and you just say, okay, I take that variation. That goes in this direction. So that's like your C of epsilon. So that C of epsilon is defined by the property that you take epsilon to the root of epsilon. You define the C of epsilon as the solution. Yeah, so it's like that guy here is a vector field along the curve, right? That's like the shear. Yeah, so like you have like this one is the green one is the vector field. Now you choose like this family of curves, such that if you take the derivative in epsilon direction, you get this green. Okay, let's continue. So there's certain special properties that we get, or like coordinates that we get, that are defined via geodesics. So coordinates via geodesics. And they are sometimes called geodesic polar coordinates. And the idea is like very similar to the case where we have like polar coordinates in the plane, where we say like one of them is like an angle, and the other one is like the radial part, and the radial part has the property that it's like the straight line, that it's like goes out to infinity in a certain direction. And similarly, something like this will be given in terms of geodesics, is like where one parameter will change what kind of geodesic I am on, and then the other parameter is like how far do I run along that geodesic. So that's the main idea. So the ingredient is that similar to the uniqueness and existence theorem for parallel transport, we can show that there is a unique geodesic starting at a given point in a given direction. Which is just like a mathematical way of saying that if you stand somewhere on a surface, that's the starting point, and someone gives you a direction and says like, let's go, and you just say like, okay, I'm just slowly walking in this direction with this velocity that is given by this vector. And like the way that I walk is like that it's in this direction of a geodesic. And that allows us to have the following definition, that for a point on a surface, differential map is a map that is defined at the point, so it's exponential at the point. It's a map from the tangent space at that point, and actually some open subset of that, which is denoted by V of P, onto the surface. And this one is given by the property by that exponential of P in the direction of V is the endpoint of the geodesic C of V, where C of V is the geodesic curve that starts at P and has like the velocity given, and V of P is the subset of all vectors of the tangent space for which C of V is defined at least up to time t equals 1. And this is always an open neighborhood of 0 in the vector space TPS. So the picture is the following. So we have our tangent plane. Let's say that our tangent plane at T P of S. So somewhere here is our surface of our point P. And then otherwise we have the surface being kind of defined like this. So we have a surface, and at some point of the surface, we choose a point P, and then we take the tangent plane along that point. Then in that plane, we have this subset V of P that gives us vectors. So we have here our, let's say, our V, and then we project it down to the surface. So let's say that we identify this point with this point, and then that C of V, and then at some point C of V at the endpoint at 1, which is the exponential of P at V. So you essentially you have like the curved object. Like you can think of that if the picture is not totally clear. So you have like you take the tangent plane to the surface, then you draw a small subset up there, and then you kind of wall it on top. But like the walling will be so that it's given by the geodesics, is that you have to choose like the geodesic that originate in this certain direction, and then you just follow that geodesic, and that might end up like goes around, and then you end up like on the other side of the cylinder maybe. But that's like you go follow the geodesic until the time is equal to 1. And one comment for the name, you may be confused because, like, what is the exponential map there? It's like it looks very strange. Like, why is that called an exponential map? Is the following: you can think of the real numbers as the tangent map to the circle, or so the real numbers we identify